Welcome to one of the most fascinating puzzles in modern physics, the strange behavior of tiny droplets that seems to break the laws of thermodynamics. At the nanoscale, tiny droplets exhibit bizarre properties, negative heat capacities and non-extensive entropy. These phenomena challenge our fundamental understanding of thermodynamics. Let's first understand what makes droplet thermodynamics so puzzling. In normal thermodynamics, when you add heat energy to a system, its temperature increases. This seems like common sense. But for small droplets, something bizarre happens. You can add heat energy, and the temperature actually decreases. This is the negative heat capacity phenomenon. Heat capacity is defined as the change in heat divided by the change in temperature. For small droplets, this heat capacity can be negative, which seems to violate our intuition about how energy works. This graph shows the difference. The green line shows normal behavior. More heat means higher temperature. The red line shows droplet behavior. More heat can mean lower temperature. The key to understanding this puzzle lies in the competition between bulk and surface effects. In large macroscopic systems, the bulk properties dominate. The interior of the material determines its behavior. But in nanoscale droplets, surface effects become extremely important because the surface-to-volume ratio is huge. The surface area-to-volume ratio scales as 3 over r, where r is the radius. As droplets get smaller, this ratio explodes. In a small droplet, a large fraction of molecules are at the surface. These surface molecules have different energies than bulk molecules because they have fewer neighbors. Let's consider a concrete numerical example with a water droplet to see how dramatic this effect is. For a 1 nanometer radius droplet, the surface-to-volume ratio is 3 billion per meter. Compare this to a 1 millimeter droplet with only 3,000 per meter. That's a million times smaller ratio. The negative heat capacity arises from a competition between kinetic and potential energy. The total energy is the sum of kinetic energy, which is related to temperature, and potential energy, which comes from molecular interactions. The kinetic energy is 3/2 nkt, where n is the number of molecules, k is Boltzmann's constant, and T is temperature. The potential energy is proportional to minus n squared over V. The negative sign indicates attractive interactions between molecules. Here's a crucial question. What happens when we add energy to a small droplet? The answer is that the droplet can evaporate molecules. This is the key to understanding negative heat capacity. When heat is added, molecules with the highest kinetic energy escape. This removes hot molecules and leaves behind cooler ones, decreasing the average temperature. Let's work through the mathematics to understand this precisely. The total energy is 3/2 nkt minus alpha n squared over V, where alpha represents the interaction strength. For a droplet in equilibrium with its own vapor, we need to consider the chemical potential. The chemical potential of molecules in the droplet must equal the chemical potential in the vapor phase. The chemical potential is the derivative of energy with respect to the number of particles. Taking the derivative, we get 3/2 kT minus 2 alpha n over V. When we add heat while maintaining equilibrium with the vapor, the chemical potential stays constant. The fundamental thermodynamic relation is dE equals TdS minus mu dN. Working through the calculus, we find the heat capacity is minus 3 nk over 2, which is negative. Let's calculate actual numbers for a realistic water droplet. Consider a droplet with 1,000 water molecules. The heat capacity is approximately minus 2 times 10 to the minus 20 joules per Kelvin. The negative sign is the crucial feature. The second puzzle is that entropy doesn't scale linearly with system size, violating extensivity. In normal thermodynamics, entropy is an extensive quantity. If you double the system size, you double the entropy. Mathematically, the entropy of 2 n particles equals twice the entropy of n particles for extensive systems. But for droplets, entropy is non-extensive because surface contributions don't scale the same way as bulk contributions. The total entropy has 2 parts, bulk entropy and surface entropy. Bulk entropy scales linearly with n, but surface entropy scales as n to the 2/3 power. This graph shows the difference. The green line is perfectly linear, representing extensive behavior. The red curve deviates from linearity due to surface effects. This brings us to the central question: do these anomalies mean thermodynamics is wrong at small scales? The short answer is no, we don't need to rewrite the fundamental laws, but we do need to be more careful about how we apply them. The fundamental laws of thermodynamics still hold perfectly well. The first law, conservation of energy, remains valid. Change in energy equals heat minus work. The second law, entropy increase, also remains valid for isolated systems. The key insight is that small systems exhibit significant fluctuations that are negligible in large systems. So what really changes when we go to the nanoscale? The answer is that the choice of statistical ensemble becomes crucial. Different ensembles can give very different predictions. In the canonical ensemble with fixed particle number, we don't see negative heat capacity. But in the grand canonical ensemble where particles can exchange, we do. Let's develop a physical intuition for what's really happening in these systems. Here's a helpful analogy. Imagine a leaky water balloon that represents our droplet. When you heat it up, water molecules evaporate and escape through the leak. The highest energy molecules are the first to leave because they move fastest and escape most easily. The remaining water actually gets colder despite the heat input because you've removed the hottest molecules. The fast-moving molecules escape while slow-moving molecules remain, naturally lowering the average kinetic energy and thus the temperature. This phenomenon is actually evaporative cooling, the same process that cools your skin when sweat evaporates. When you sweat, the most energetic water molecules evaporate from your skin, taking their energy with them and cooling you down. Let's work through some realistic quantitative estimates to see how significant these effects are. Consider a specific example, a sodium cluster containing 100 atoms. This cluster has a radius of approximately 1 nanometer. At room temperature, around 300 Kelvin, the surface energy is approximately 10 electron volts. The thermal energy kT is about 0.026 electron volts. The ratio of surface energy to thermal energy is about 400, showing that surface effects completely dominate. This enormous ratio means surface energy completely dominates over thermal energy for such small systems. We can estimate the magnitude of the negative heat capacity. The absolute value of heat capacity is about 100 times Boltzmann's constant, or 10 to the minus 21 joules per Kelvin. These aren't just theoretical predictions. There's strong experimental evidence for these effects. Experiments on metal clusters, particularly sodium and potassium clusters, have directly measured negative heat capacities. These measurements use sophisticated mass spectrometry techniques to study individual clusters. Mass spectra show characteristic distributions with peaks corresponding to particularly stable cluster sizes, called magic numbers. Gold nanoparticles also exhibit these anomalous thermodynamic properties, which has important implications for nanotechnology. Because you can't stick a thermometer into a nanometer-sized particle, temperature is measured using clever indirect methods based on emission spectra. We can understand these phenomena through the lens of phase transitions. Droplet evaporation is analogous to a first-order phase transition, like ice melting to water. Particles exchange between the droplet phase and the vapor phase. At the phase transition point, both phases coexist in equilibrium. Molecules constantly exchange between liquid and vapor phases, maintaining dynamic equilibrium. The latent heat is the energy required to move a molecule from the liquid to the vapor phase. Latent heat L equals the energy per molecule in vapor minus the energy per molecule in liquid. For water droplets, the latent heat is approximately 0.4 electron volts per molecule. These peculiar properties have important implications for nanotechnology and our understanding of nature. In nanoparticle synthesis, temperature control becomes extremely tricky because of these non-standard thermodynamic behaviors. In atmospheric science, understanding cloud droplet formation requires accounting for these nanoscale effects. In biology, protein folding involves relatively small systems where these effects can matter. Nanoparticles surrounded by their local environment exhibit complex thermodynamic behavior that depends on their size and interaction with surroundings. In drug delivery systems, nanoparticle stability is crucial and depends on understanding these thermodynamic principles. Here's an important question. Should engineers designing nanosystems worry about these effects? The answer is yes. particularly for systems smaller than about 10 nanometers. These effects become quantitatively important. How do theorists resolve the apparent paradox of negative heat capacities? The key theoretical insight is to carefully distinguish between different statistical ensembles. In the microcanonical ensemble, energy, particle number, and volume are all fixed. Entropy is a function of energy, particle number, and volume. Temperature is defined as the derivative of entropy with respect to energy. 1 over T equals partial S partial E. This microcanonical temperature can actually decrease as you add energy, giving negative heat capacity in other ensembles. This graph shows how temperature can have a maximum as a function of energy. Beyond this maximum, adding energy decreases temperature. In the canonical ensemble, we fix particle number, volume, and temperature instead. In this ensemble, heat capacity is always positive because we've defined it differently. The paradox resolves when we realize that different ensembles describe different physical situations with different behaviors. Let's summarize what we've learned about the droplet thermodynamics puzzle. Small droplets exhibit negative heat capacity and non-extensive entropy due to the dominance of surface effects. These phenomena arise fundamentally from how the surface-to-volume ratio scales with size. The laws of thermodynamics remain completely valid, but require careful consideration of ensemble choice and boundary effects. The key physical mechanism is evaporative cooling, where high-energy molecules preferentially escape. Heat input drives evaporation, which causes net cooling of the remaining droplet. These effects become quantitatively important for systems smaller than about 10 nanometers. Understanding these principles is crucial for nanotechnology, biological systems, and atmospheric science. At the microscale, thermodynamics reveals rich and subtle behaviors that challenge our macroscopic intuitions but deepen our understanding of nature. The final message is that nature becomes wonderfully subtle at small scales, requiring us to think more carefully about concepts we take for granted in everyday life.